Hello everyone and welcome to this lecture in the hands-on large language models series. Today we are going to be looking at a very interesting topic, and that is the topic related to memory. We as humans, all of us know about memory. In fact, when we have a conversation with people, we rely a lot on memory. Let's say you're interacting with someone, and that interaction is for 25 minutes or 30 minutes. Although you probably don't exactly remember what that person has said in the first 5 minutes, you do have a general idea of what the conversation has been about. So, to have conversations with people like humans do, large language models also need to have memory. And this is not an easy thing to do because ultimately you have to think that a large language model is not a human, right? It's just a architecture with a huge number of weights, with a huge number of parameters. And so it's a bit of a challenge to help large language models to remember conversations. Now, to all of you who have been using ChatGPT, you might think that why is this a problem? Because when we interact with ChatGPT, ChatGPT seems to remember what we have earlier told it, right? You can have a long conversation with ChatGPT and it will remember what you have said previously. And that's true with this product. Remember, there's a different difference between models and product. ChatGPT is a product, but when you are dealing with large language models on the Google Colab interface, they do not directly have memory. And that also depends on the type of large language model which you use. Some large language models by default do have some memory, whereas the models which I'm going to show you today, and that's Microsoft Phi 3, it does not have any memory. So, what I'm going to teach you today is techniques which help large language models to remember previous conversations. So, let's get started with today's lecture. By default, when we directly use large language models, they will not remember what was being said in a conversation, especially if you are coding using the Google Colab interface. You can share your name in one prompt, but the large language model would have forgotten it by the next prompt. And before we get started, let me actually show you a quick demonstration of this. So I'm on my Google Colab interface right now, and the large language model which we are using is this Phi 3 Mini 4K Instruct FP16.gguf. So let me show this model to you right now. This is this model. So what does gguf mean? It means that we have a quantized version of the model and we are using FP16, which means we are quantizing from a floating point 32 to a floating point 16. What does 4K mean? 4K is the context size of the large language model. And I generally like to start out with this Phi 3 Mini 4K because it's a small model. It's 3.8 billion parameters and it does not take too much amount of memory on your local machine. This is the large language model which we are utilizing in today's lecture. Okay, so we have loaded this model right now, and to load this model and to perform inference using this model, we are using a framework called Llama CPP. So if you Google Llama CPP, you will see that it's a large language model inference framework which is written purely in C++, because of which it's extremely fast and you can query or you can run inference on a wide range of large language models using Llama CPP. So this is the tool which we are going to use in today's lecture. So what I've done over here is that from LangChain, I've imported this package called Llama CPP, and then we using Llama CPP, we have provided the model path which we are going to use. Recall that starting from the previous lecture, we have started using LangChain a lot. And in the previous lecture, we have seen that one of the major advantages of LangChain is that we can chain multiple components together. And today you're going to further see this advantage because one more such component which we are going to chain today is the memory component. So LangChain is the framework which will be extremely useful for us in today's lecture as well. Okay, so here you can see that from LangChain we have imported the Llama CPP application and we have downloaded the large language model. And now we can start testing the large language model. Before we go ahead with the memory part, first let us create a simple chain. And this is the chain which we are going to create using LangChain. I am going to create a chain which has a prompt, and the prompt is then chained to my large language model. So this is a simple single chain I'm going to create using LangChain, and then later we'll see how to add another components to it, such as the memory components, etc. So for now, as you can see, we will create a simple chain with a prompt and attach the prompt with the large language model. So the LLM part of this we have already defined before, right? But for the prompt, we'll have to start with a template. So since we are using Microsoft Phi 3, there is a specific template which is expected. And for this template, we start with a string. Then the user prompt has to be given in this input prompt. And then we have to mention end, etc. And then the assistant response, which is the LLM response, will be provided later. So the template just needs to be written once, and we have to create a prompt template. So then the only variable needed from the user side to create a prompt is just the input prompt, and then we can use the prompt template to automatically format the prompt into the format which is expected by Microsoft Phi 3. Alright, so now I have created this chain which chains my prompt with the large language model, and then you can use basic chain.invoke. What this does is that this invokes the chain, which means that you can now give the input prompt and you will receive the answer. So when you call in the invoke, what happens is that you have to provide the input, and then the output will be provided through the what's the output of the chain in LangChain. So now the input prompt which I'm mentioning is, hi, my name is Martin, what is 1 plus 1? And you will see that the response is, hello Martin, the answer to 1 plus 1 is equal to 2, which means now the chain is invoked and the chain is giving us an answer. So recall what we are using here. We are using the framework called LangChain to combine the prompt module with the LLM module. And we are using an open source LLM called Microsoft Phi 3 Mini. And thirdly, we are using quantization to make sure that the model does not take too much memory on our device. I want to mention here that this code has been borrowed from this book, Hands-on Large Language Model, which is written by J. Alamar and Martin. This is an awesome book which I have been referring to recently. All right, so we have constructed the prompt, right? Now, remember what we started this lecture with. I want to illustrate memory, right? And I want to illustrate to you whether LLMs remember what we are saying in a conversation. So let's do a simple example here. So again, I'm going to use basic chain.invoke, and I'm going to give the same prompt. My name is Martin. What is 1 plus 1? In fact, maybe let me change this a bit, or let's use the same thing. Hi, my name is Martin. What is 1 plus 1? And then the answer given by the large language model is, hello Martin. The answer to 1 plus 1 is 2. Good, no problem. And then let me ask the LLM to reproduce the name. So then I do basic chain.invoke input prompt, what is my name? And then the LLM says that I am unable to determine your name as I don't have the capability to access personal data. However, if you are looking for guidance on how to find out your name, it might involve checking recent documents. Now the thing here is privacy, of course, is an issue here, but the LLM also is not retaining memory. If it were to retain memory, it would have mentioned that my name is Raj. And you can try doing this with ChatGPT. Let's say my name is Raj. What is 1 plus 1? And then it says 1 plus 1 is 2. So let me ask 2 to 3 more questions, and then let me test the memory. So let me ask what is 1 plus 2 again. Then let me ask what is 1 plus 4. And now let me test the memory by asking what is my name. So you see here ChatGPT retains the memory, and here it says that you mentioned earlier that your name is Raj. But the memory retention is not happening using our Google Colab code, because as I mentioned, this is not yet a product. It's just a model which we are using for inference. So somehow we need to do something to add a memory block, right? And these are the techniques which I'm going to discuss with you today. Right now we are at a stage where without memory, if you ask what was my name again, it says that I don't have access to personal information. We want to move to left to the right. where somehow the memory is stored, and when we ask what was my name again, it will say that your name is Martin. So in today's lecture, we will see how to go from left in this image to right. And here is again where LangChain comes into the picture, right? The simplest way to visualize this is we have a prompt at this moment and we have connected the prompt with an LLM. Okay. Now what we need to do is that we need to take this chain and we want to break this chain over here and we want to add another module, which is the memory module. We want to add the memory module. So then the chain will be prompt followed with the memory, and then the entire input with the memory or the history will go to the large language model, right? When we say memory, it's also sometimes referred to as history, the conversation history or the chat history, that term you might be more familiar with. So there are actually three different ways of giving memory to large language models, and here is where we differ from humans. If humans lose their memory, it's extremely hard to reprogram the neural network in the mind to gain back the memory. But large language models are computational frameworks. So it turns out by just adding these memory blocks, LLMs can retain memory. So the three ways to give memory to LLMs are: first, there is something called as a conversation buffer, and there are two types within this. There is a normal conversation buffer and there is a windowed conversation buffer. We'll learn about this. So these are two techniques, and the third technique is conversation summary. All of these techniques are extremely intuitive to understand, but you will just see how those are implemented in code. I hope all of you are with me until this point and you have understood the problem and what we are trying to solve here. So let's try to understand these solutions one by one. The first thing which we will try to understand is the first technique, which is called as the conversation buffer. So conversation buffer is simply reminding the large language models what has happened in the past. So imagine you're talking with a friend, right? And the friend is not remembering what was said before. What will you do? You will just remind them everything of what has happened in the past. So it's like collecting the information of the past and providing it to the large language model so that it can retain or recollect the past. Imagine you're chatting with someone and there is the feature of copy chat history or save chat history, right? You can think of conversation buffer as something like that, chat history. So what we are going to do when we add conversation buffers in the chain of LangChain is that we will copy the entire conversation history and we will paste it into our prompt. So to give you an understanding of what this would look like, imagine the prompt which I'm giving is what is my name, right? So let's say initially I ask what is 1 plus 1, and then the LLM answers the answer to 1 plus 1 is 2. The next prompt which I give is what is my name. Now when this prompt is given to the LLM, along with this prompt, it's also given the entire conversation history of what has happened before. So now the prompt consists of two things. The prompt consists of the input text. The prompt consists of the input text, and the prompt also consists of the chat history or the conversation history. So this blue block which I have shown here is the conversation history, and in the conversation history it will be stored that earlier we have asked ChatGPT, my name is Martin and what is 1 plus 1, and then the LLM, and then the LLM has answered, hello LLM, hello Martin, the answer to 1 plus 1 is 2. This entire history is also provided along with the next prompt. So now the prompt consists of all of these two things. And then when the LLM answers, of course, it's going to remember what was asked in the past because that's now included in the prompt. So this is a kind of a trick which we play where we augment the prompt with the history, right? So as you can see here, we can remind a large language model of what previously happened by simply appending the entire conversation history to the input prompt. Now, if LangChain was not there, you probably would have to code this out from scratch. How are we going to append the history to the prompt, etc.? But LangChain takes care of this because in LangChain there is an object, or this form of memory in LangChain is simply called as conversation buffer memory. And using this conversation buffer memory, we can easily tell the LLM that along with taking the prompt, you also have to take the conversation history into account. So if you search conversation buffer memory LangChain, right, you will be taken to this page which talks about the conversation buffer and how to use conversation buffer memory. We are just going to see that in action right now. So let's just jump into code and let's see what are the changes which we need to make to define the conversation buffer memory. Okay, so now one thing which I want to start out is that I don't want to start with this first piece of code. I want to start with the second piece of code because that way it's more intuitive, right? So what did we know that, or what's our intuition? Until now we have the prompt, right? And we have the LLM. But now we want to add one more thing to this chain, and that's the memory. So now this is the full chain which we want to create. This is the entire LLM chain. So let's see how to do that. So from LangChain you have to import two things. So from LangChain.memory you have to import conversation buffer memory, and from LangChain itself you have to import the LLM chain which creates the entire chain. Then you have to define memory. So there are different types of memory. We are going to be using conversation buffer memory, and you have to mention the memory key. That is very important. So here we have to mention the memory key. You can give it any name which you want, but the key name which I am using right now is chat history. So what this will essentially do is that you can imagine the memory to be arranged in a system of lockers, right, where you store money. Let's say these are the lockers, and every locker can be unlocked only with a specific key. To unlock the memory, the key which is needed is called as chat history. So if you give this key over here called chat history, if you provide the key called as chat history, then that simply means that the memory will be unlocked or the chat history will be revealed. So that's why this memory key is going to be very important. And then we create the chain. So the chain is a combination of the prompt, the LLM, and the memory. Three things, exactly what we had seen over here: the prompt, the LLM, and the memory. That is the chain. All right, so now the LLM chain has been created, and now we can see how to create the prompt template. So now you see the prompt template earlier was a very simple prompt template which we used, which was just user input prompt and then the assistant, right? But now we have to change it up a bit. We still have the user, we have the input prompt and the assistant, but there is one more thing which is added before the prompt, and that is the current conversation. And the current conversation takes the chat history. Now what is chat history? That is specified by the input variables. So the input variables of course will be the input prompt which is given, and it will also be the chat history. Now you see this chat history here matches the memory key. So when the prompt is defined and the input variable chat history is shown, what will happen is that the LangChain or the LangChain object which we are defining, that will go to the locker. It will use this key called chat history and it will unlock this memory over here. So memory will be unlocked, or the past conversations will be unlocked, and those will be attached to the input prompt. So after the locker is unlocked, the memory is retrieved. That memory is coupled with the input prompt. And so now the prompt which is given to the LLM consists of the memory as well as the input text. Both are combined. Both are combined using this template. So the input prompt is the input text, which is the first component of what we saw over here. That is the input prompt, and the chat history is the second component, which is retrieved from the locker using the memory key. All right, so now we have created everything. We have created the prompt template, we have created the LLM chain. Now all we have to do is just define the prompt and we have to invoke the chain, and let's see whether history has been retained. So now I'm just going to do LLM chain.invoke, and I've defined the input prompt to be, hi, my name is Martin, what is 1 plus 1? When you invoke this, you will see three objects being printed. The first is of course the input prompt is printed, chat history is printed, and the text. So the output is hello Martin, the answer is 1 plus, answer to 1 plus 1 is 2. That's fine, we have obtained this answer before also. What we are interested is in the chat history. Since this is the first prompt, the chat history will be empty. When you start interacting with it from the second time, the chat history will be appended. Now let's ask this question, what is my name? Remember earlier we had asked this question and it did not answer, but now let's see. So the second prompt which I'm giving is, what is my name? Now see, what will happen here is that when I give this prompt, uh, along with this input text, the chat or the conversation history previously will be appended to this prompt. So if you run this, let's look at the output. So here you see the LLM is saying your name is Martin, as mentioned in the beginning of this conversation, which means it clearly retains memory, right? How do I know it retains memory? Because check out this chat history. The chat history now is the entire chat conversation. So first the human, which is we asked, hi, my name is Martin, what is 1 plus 1? Then the AI responded, the answer to 1 plus 1 is 2. How can I assist you with further topics? So now in the chat history, the LLM has what I had asked before and what answer the LLM gave. It has both these things in the chat history. So when the next prompt is asked, it has the chat history with it along with the prompt. So when you ask what is my name, it already has this chat history, right? So it says that your name is Martin, as mentioned in the beginning of the conversation. That's how chat history, or that's how memory is given to the LLM using the conversation buffer or conversation buffer memory. This is a good schematic to see what is happening. So these are the first set of prompts, right, which you gave. Those then become the conversation history. Then you ask the next prompt, and then the conversation history is utilized to give you the output, which is that it recollects memory that your name is Martin. It's a very simple and an intuitive thing to understand, but one more thing which you learn from here is the power of LangChain again. You see, what we did is we just simply chained the memory here, right? So chains work very well because you can keep on adding multiple things in the chain. Later you will see that we can add agents also very easily in this chain itself. So this is how LLM chains work, and this is how memory, this is the first way to add memory to large language models. Already you must be seeing some problems with this approach, right? Because imagine what will happen if you keep on interacting with the LLM for a long period of time. The history will keep on getting appended and it will be a huge prompt. Now the problem here is that if the context window of the large language model is less, then all of these prompts will not fit in the context, and that will lead to outputs which are not efficient. That's one of the major disadvantages of conversation buffer. It's that the prompt size goes on increasing to a huge amount, and that's why we need LLMs with a larger context size if we are going to use conversation buffer. One workaround to this is the second method which we are going to discuss, and that's a windowed conversation buffer. The windowed conversation buffer works exactly the same way as the conversation buffer memory, but there is one small change. And that change is that we only use the last k conversations instead of maintaining the full chat history. So in the conversation buffer, the entire chat history is maintained. We do not limit it to only 2 conversations or 3 conversations. But in windowed conversation buffer, only the last k conversations are maintained in the memory. Now this is where it gets very weird to compare this with humans, because imagine talking to a friend of yours who only remembers last 2 conversations of what you are speaking and who does not remember anything what has happened before. It's very weird to think of this, right? But it's just a way to work with the computational limitations of the models which we are dealing with. So the way to use this windowed conversation buffer using LangChain is something called conversation buffer window memory. So first we saw conversation buffer memory. Now we can see conversation buffer window memory. And then you will see this in LangChain. I'll provide links to all of this in the information section. But you will see that here we have to define the K, which means how many conversations should the LLM retain the memory. So let's code this out right now in Google Colab, conversation buffer memory window. And very similar to the code for conversation buffer memory, we have to import a package from langchain.memory, and this package is called conversation buffer window memory. So from langchain.memory, I am importing conversation buffer window memory, and then everything is the same. We still have to define the memory key to unlock the locker. But the only difference is that we have to mention this k. This k is the number of conversations which we want the LLM to retain, right? So now I've mentioned k equal to 2, which specifies that retain only the last two conversations in memory, not more than that. That's it. And then we define the chain the same way. It's the prompt combined with the LLM combined with the memory. Actually, there is only one line of change to use a buffer memory window, and that's specifying the key. Now let's test this out. What I'm going to do is that I'm going to give two prompts in succession with each other. And remember, the LLM will only retain two conversations, so it should retain the history of these two prompts. So the first prompt is, my name is Martin and I'm 33 years old. What is 1 plus 1? And the second prompt is, what is 3 plus 3? Okay. So let's see, I'm invoking the chain two times with these two prompts. So the input prompt now is, what is 3 plus 3, which is the latest prompt. And then the answer is that the sum of 3 plus 3 is 6. But let's look at the chat history. The chat history consists of, my name is Martin, 33 years old. What is 1 plus 1? And for the first answer, the LLM says that my name isn't programmed to remember personal details like age, but I can certainly help you with your maths question. And then it says the answer plus 1 is 2. The answer to 1 plus 1 is 2. So it answers what we have mentioned, and that's stored in the history. And for the second question, it answers the sum of 3 plus 3 is 6. And that also will be stored in history, because the two conversations will be stored in history. Now let's test this one thing. Now I'll ask one more prompt, which is, let's say the input prompt is, what is my name? And here you will see that check whether it knows the name that we gave it. So what is my name? And the answer is that your name as provided in the conversation is Martin, because this is now stored in the history. See, the history consists of the name. And then it mentions the name, so that is good. But now what I can do is that I can actually ask one more question, which is, what is my age? Now this won't be stored in the history, because it is the first question which I asked. See, and after that I asked two questions which will be stored in the history. So what is 3 plus 3? The answer to that will be stored. What is my name? The answer to that also will be stored. But the answer to the first conversation or the first prompt will not be stored. And the age was only mentioned in the first prompt. Why will it not be stored? Because k equal to 2. So only the history of two conversations will be stored. And those two conversations are when the user asks, what is 3 plus 3? And when the user asks, what is my name? Only those two will be saved. The input and even the output of the first query will not be saved. So when you ask, what is my age, you will see that the answer which the LLM gives is that I am unable to determine your age without specific data or context shared during our conversation. So see, clearly the age is not getting retained here. This is what we wanted, right? Because we only ask the LLM to store the history for two conversations. What you can do now is that you can put k equal to 3 here. You can try to run this on your own, and then you can try to ask, what is the age? And then you will see that when you ask, what is my age, it will be able to recollect the age, because now you have asked the LLM to retain the history for three conversations. So the three conversations, of course, include the first one which you had asked, in which you had actually mentioned your age. So let's actually see the answer to this now, which I'm running live. See, now the text is, hello again. As per the initial information you provided, you mentioned that you are 33 years old. So now it retains my age because I have mentioned k equal to 3. So the history of the past three conversations is now retained with the large language model. This is how you can ask the LLM to only retain specific amount of information of what has happened in the past. And this will also free up computational memory. It won't increase the context size too much. But of course, the disadvantage of this is that it limits the uses, right? If let's say you're developing a chatbot, and if the client is interacting multiple times, you don't just want to retain what has happened for two conversations before, right? You also want the chatbot to remember what the client asked at the start. Otherwise, it's not a very useful chatbot. So again, you see there is a trade-off between computational memory and the how good you want the model to be. How better, the better the inference you want, the more history you need to ideally retain. But that will also lead to more computational time and memory. So with large language models, there is always these trade-offs. You will never get a clean solution which optimizes for everything. But the real test of an LLM engineer is how you work with these trade offs and what do you prioritize. Many times it comes, if you're working in a company, it will come down to revenue, it will come down to how much cost it will incur to you, how much cost you can bear as a company daily, how much revenue you are getting from this product, and all of these considerations have to be made. All right, and now what we can do is we can come to the third technique to retain memory or to give memory to large language models. And this third technique is called as conversation summary. This is actually a very interesting thing, right? Because I think this is the closest to what actually happens in humans. If I'm interacting with someone for 2 hours, let's say, or 3 hours, if I'm on a podcast and if I'm interacting with someone, I will not exactly remember what they said earlier. I will not exactly remember the sentences which they used. What my mind will do is that my mind will form a condensed representation of what they have said. Those might be bullet points in my mind, or those will be a summary of what has happened. And then utilizing that summary, I will respond later. So, although I might have missed exactly the sentences, what they have said, the grammar which they have used, I still have a gist of what that person has said because my mind is good at summarizing what has happened before. So, the third technique which we are going to see, conversation summary, I actually believe this is closest. This is closest to how humans uh, retain memory or humans operate in conversations or in long conversations. It's also a very interesting technique because what's actually done here is that the entire chat history is taken and then we summarize it. The window is not used here. The window buffer, in the window buffer, we only look at some previous conversations, right? In the conversation summary, we look at the entire chat history, but instead of giving it word by word in the prompt, or instead of appending it word by word in the prompt, the chat or the conversation history is summarized into key points and then it is added to the prompt. So now the prompt will consist of the input text for sure, and the second aspect of what the prompt will contain is that it will contain the conversation, or rather I should say it will contain a summary of the chat history. You see how this solves the problem of the memory, or the computational memory rather. If you keep on using chat history for previous 100 conversations, the history will be very long and the prompt will be very long. But if you are just summarizing, you can still use the data from 100 or 200 conversations before. You can summarize it and append it to the prompt. That will reduce the computational memory needed by your large language model, but at the same time you will retain history. So I think this is a good balance between saving computational memory but at the same time not letting go of history in the past or not letting go of the conversations in the past. Now, who generates this summary? This summary is generated by another large language model. So there are two LLMs actually which can be used here. One LLM specifically for generating the summary, and the other LLM, of course, which processes our input text. So let's see the schematic here. Again, let's say I have asked I'm Martin, what is 1 plus 1? And the answer to 1 plus 1 is 2. Now, instead of taking this entire thing word by word, we summarize it using another large language model, and the conversation history, we add the summary. What you see in the red here, this is the summary, and then that summary is then appended to the prompt, the next prompt. So as I said, the next prompt consists of the input text and a summary of the chat history. So there are actually two calls which are being made. There is a user prompt which is asked to one large language model, and there is a summarization prompt which is asked to another large language model. So this summarization LLM, what it will do is that it will take all the previous history and then it will create a summary of it. and then it will feed this summary to the LLM which deals with the user prompt. So to use this approach in LangChain, we first need to prepare something which is called as summarization template. So what the summarization template will do is that it will be used as the summarization prompt for the LLM which is going to do the summary. So let's now see this in action. Yeah, so here's the third technique which is called as conversation summary, and this is the summary prompt template. So the summary prompt template is different than the input prompt template. So this summary prompt template just says that summarize the conversations and update with the new lines. Again, we are using Phi3 as the LLM for this. You can feel free to use a different LLM for this. We don't have to use the same LLM for the summary and also for the input prompt. But for the sake of simplicity, I'm using Phi3 here again. So I'm saying summarize the conversations and update with the new lines. I of course provide the current summary and then I provide the new lines of conversation, which is how the user has interacted, let's say, with the chatbot. And the new summary will then be printed out. The input variables here are new lines and the summary. So let me tell you where these input variables come from. So now the package which you need to import from LangChain is called conversation summary memory. And here you have to pass the LLM for sure. You have to pass the memory key and you also have to pass the summary prompt. So see, until now we have looked at this LLM chain where we pass the prompt, where we pass the LLM and we pass the memory, right? And until now the memory which was defined was just using one line. But now you see how the memory is defined. In the definition of the memory also we have three things. We have the LLM which we have to use. That LLM will create the summary. So this is the second LLM. This is the second LLM which creates the summary, right? Then of course we use the memory key. This part is the same. This is the key which will open the vault and retrieve the memory from inside. It is the same as before. The another difference is that here we have to give a prompt, which is the summary prompt, what I showed you before. And then the new lines and summary which have been mentioned here will be automatically taken from the way conversation summary memory is defined using LangChain. So the difference between conversation summary memory and the earlier memories is that earlier we just have to mention the memory key. That's it. But in conversation summary memory, we have to mention three things. We have to mention the LLM, which will do the summarization. We have to mention the memory key, and we also have to mention the summarization prompt. So that's how the memory is defined. And then we have to, of course, do the LLM chain. That's the same thing which we have been doing earlier. Let me show you the schematic of that chain. Yeah, this chain. We'll chain the prompt with the LLM with the memory, right? So the LLM chain has been defined here. But I want you to focus on how the memory is defined here. That is the only difference between using conversation summary memory and the windowed buffers or the buffer memory which we used earlier. Now let's see. So I'm generating two prompts here. My name is Martin. What is 1 plus 1? And then I'm asking what is my name. So again, there are three outputs which are produced. The input prompt, which is what is my name. Now see how the chat history is produced. A summary is produced now. Human named Martin asked AI about the result of 1 plus 1 and it receives a response confirming that the 1 plus 1 is equal to 2. So you see the chat history now does not just contain the prompt and earlier answer just as it is. A summary is mentioned. And then the answer is your name is Martin. So you see the history is now retained. Even this we were not able to get earlier. But now the name is being correctly called out because it has been stored as a summary in the chat history. Then let's say I ask what was the first question I asked. The answer is again correct. The first question you asked was what is the sum of 1 plus 1. Now how does it know it is the first question I asked? Because look at the summary which it has stored. The summary which has been stored is in a conversation human named Martin inquires about the sum of 1 plus 1 and then receives information from the AI that it equals to 2. The AI also offers further assistance and acknowledges Martin's name as mentioned in the discussion. Because the second question which was asked is what is my name. So from this summary, it's very easy for the LLM to understand what was the first question I asked. because it can just say that the first question you asked was what is the sum of 1 plus 1. In it guesses that from the summary. That's incredible, right? We can use any amount of chat history using this conversation summary memory, and it will always boil it down to a condensed form like this. Of course, there are disadvantages again in this method, because the quality of the summary depends on the second large language model which you are using, and some information is always lost. So let me say that here itself. Even when you are summarizing, some information is always lost. So some info is always lost when you make the summary, right? That's of course the disadvantage. So as I mentioned here, the possible disadvantage is that the original questions are not fully saved. So sometimes the models need to infer it from the context. Remember, the model does not have the entire history as it is, right? It only has the summary. So if the summary has lost some information, the model probably will give wrong answers. So you see, every possible method has its advantages and has its disadvantages. But I personally like the summarization memory a lot because it's closer to how humans operate, and it's a good trade-off between having a low computational memory. It has a low computational memory and reasonably decent answers by considering everything in history, not letting go of something in the past. Uh, Okay, so now you can even print out the memory here, you can print out the chat history, and you can see the summary which is retained. This brings us to the end of our lecture, where we discuss three types of ways in which you can add memory to large language models. The first is called as conversation buffer, the second is called as windowed conversation buffer, and the third is called as conversation summary. There are pros and cons of each of these. For conversation buffer, the pro, which is the important highlight, is that it's very easy to implement and it ensures no information loss because we directly use the history as it is. The disadvantage, of course, is that it's slower generation speed because the prompt becomes huge. And another major disadvantage is that it's only suitable for large context LLM, because if you have an LLM whose context size itself is low, the prompt as it becomes huge, it won't even fit in that context. And larger chat histories make information retrieval difficult. Those are the disadvantages. Windowed conversation buffer, it solves the problem of large context windows are not needed because we are only looking at few conversations in the past. And another advantage is no information loss over the last k interactions, because we are not doing any summarization here, we are directly taking the prompts as it is. The disadvantages are that it only captures the last k interactions. It has no information of what has happened in the past, and I think this is one major disadvantage, especially if you're developing applications like chatbots. Now, the third type, conversation summary, of course, the pros are it captures the full history, it reduces the tokens needed to capture full history. So again, it solves this large context size issue. But the cons is that we need to make an additional call, which is for the summarization prompt. So that increases the cost if you are deploying this in product settings. And of course, the major disadvantage is that you have to rely on the LLM summarization capabilities. So I personally think that if you want to develop a production level chatbot by retaining history, you should not go with the windowed conversation buffer. Either go with conversation buffer or go with conversation summary. If you have the budget, you should definitely go with conversation buffer. You can estimate how long do customers usually interact with the chatbot, and you can make an estimation of whether that will fit in your context size and how much cost it will be for you. But if you are tight on budget and if you still want to include the entire history, you can go with conversation summary. That's probably the best option to go ahead with. Thanks a lot, everyone. I hope you liked this lecture in which we talked about how to add memory to large language models. In the next lecture, we'll be looking at agents. This is one of the most important and a very, very trending topic in the field of large language models, and it's so important for a specific reason. I'm sure many of you are confused between LLMs and agents at this stage and don't know the difference between them. We'll see that in the next lecture, and we'll even deploy our own agent using LangChain. So thanks a lot everyone, and I look forward to seeing you in the next lecture.